So today we'll try to understand what is principal component analysis and where do we use it in industry, and what are the kind of data on which you would ideally use it, or what are the different kind of machine learning projects or workflows where you would use it. So the first question is, what is this technique mainly used for? And principal component analysis is mainly used for dimensionality reduction. So whenever you have a data set, let's say I have a data set where I have marks of students in a certain subject. Now, if I plot that data set, I will get values over an axis, right? If I plot the data set where I have marks of students in, let's say, mathematics, then it'll just be dots on a number line. That okay, these are the different marks that the students have gotten. Now, if I increase the dimension of the data, that is, if instead of just the mathematics marks, we also try to plot their science marks, then what happens is you basically need an XY plane, and you will have some value for x-axis, which is, let's say, your mathematics data, and some value for your y-axis, which is, let's say, your science data, and you will then plot a point on the xy plane. What happens if I add another subject here? Let's say I add social studies as my third subject. Now I need a three-dimensional space to make that plot, which is still doable. But once I move into 5, 6, 7, 8, 9, 10 dimensions of data, then it becomes very high to visualize it, right? So visualizing data which has a very high dimensionality is one of the main uses of principal component analysis. And then also when you are doing things like face recognition, or even when you are trying to train a machine learning model, but your data has a lot of columns, and just by having a lot of columns, your model is going to be complicated. It's going to take a lot of time to train. When you deploy this model in the real time scenario, it will take a lot of time to make predictions. So we generally try to make a machine learning model as simple as possible, and hence we often reduce the dimensions of the data. But at the same time, we do not want to lose any important information which might be hiding in the data. And that's where PCA comes into the picture. Now, how does PCA work is something that we'll discuss really quickly next. And here you see that there are some examples of applications of PCA. Face recognition and image compression are some examples. This is a very, I would say, obvious example, because if you are maintaining most of the information of the image, but at the same time decreasing its number of dimensions, or let's say here number of pixels somehow, then you are sort of compressing the size of the image, right? And we use PCA for that as well. Now, this is, I would say, a very good plot to understand how PCA works. Let's say I have two variables, x1 and x2, and I plot this variable on x1, x2 axis. So instead of xy axis, I have an x1, x2 axis, and these are all different scores, or scores for subjects of science on the x2 axis, and for the subject of maths on x1 axis. And I plot these points. Completely forget about this these two lines right now. So this is how a plot looks like. Generally speaking, this will be actually in the first quadrant, because I'm assuming that kids will not score negative marks in x1 or x2. So mostly your data will be somewhere here. You will see a lot of points here. That is how you plot the data. Now, the idea of principal component analysis is you first move the data in such a way that you center the data, and that's why all the values which were in quadrant 1 have been just picked from here and sort of moved towards this side, so that they are centered around the origin. Once your data is centered around the origin, then you try to find a line which maximizes the difference between two certain types of data. Think of binary classification, that we are trying to classify good students and students who need improvement. So there are two classes basically, right? There are some students who are good, some students who need improvement. So when you try to find the line which best separates these two classes of students, that students who are good and students who need some attention from the teachers, then you sort of get the principal component, the first principal component. Intuitively, to build an idea, imagine that you have a line which just passes through the origin. Now, there are like infinite number of lines which can pass through the origin. Okay, the line could be something which starts from this point, ends at this point. It could be like this with a much bigger slope, or it could be something like the x1 axis with a much smaller slope, or the slope is zero in this case for the x1. But why did we choose this particular line only? So we are trying to find the line which minimizes the distance. So imagine that all these points, now what you do is you start dropping perpendiculars from these points on this particular axis. So all you are doing is you are projecting these points on the y1 axis. Now we need to find that particular line which minimizes the sum of squared of these projections, right? So the line which minimizes the sum of squares of these projections is the line that we need to find in principal component analysis. That line will give us the best separation between the data of two different classes. So that becomes your first principal component, and generally the second principal component is the one which is perpendicular to the first. So y1 is your, if y1 is your PC1, then y2, which is just a line which passes through the origin and is perpendicular, will become your PC2. There are concepts like eigenvector, eigenvalues, which we'll discuss after, like if we were to get into a lot of details. I've just pulled off this PPT from the internet, and once we are having the real lectures, I think we'll try to discuss a lot of details about what these eigenvectors and these eigenvalues stand for, and how do you use it in practical sense, right? What's the use of these? One really interesting plot that I saw in this is something that you see here. So this plot basically tells you that a certain principal component, what amount of variance in your data is explained by that particular principal component. If you have a one-dimensional data, you can just make, basically it will be like an axis. So you can't have a principal component because it will coincide with the same axis on which you are plotting the data. If you have, like, let's say a two-dimensional data, then generally you will have one principal component and then another one will be the one perpendicular to it. If you have 10 dimensional data, then you will have PC1, PC2, all the way up till PC10. Generally, PC1, PC2, PC3 will have very high variance, which means that they will have a lot of information about your overall data set. And PC7, 8, 9 will just be having just 1% or 0.5% kind of information about your data set. And that's the idea, right? We want to reduce the dimension. If we already have, like, if we have a 10 dimensional data and then all 10 principal components have a very high variance, that means that all 10 principal components are sort of explaining a lot about the data or have a lot of information about the data. Let's say all of them have 10% of variance, then which one will you discard? How will you decrease the dimension of the data, right? So it's not going to work. And the whole idea of the way the principal component is calculated is to find that particular axis across which the data has maximum separability for classification, or where the data has maximum knowledge or maximum information. So it will always, if you have done your principal component analysis rightly, the graph will always be like a decreasing graph. It need not be a strictly decreasing graph, but the PC n minus 1 will always have a higher value than PC n. So that's the general idea. Now the question is, how do we implement this, right? We have understood that principal component analysis is basically bringing down the data from a much higher dimension into a dimension which is smaller. It helps us with many things. It helps us to visualize the data better. It helps us to make less complicated machine learning solution. It helps us to make more production ready machine learning solution, because if you have a lot of data while training, then during inference, when you are using that model, at that time also you will require a lot of data. So it helps us with a bunch of things. Let's quickly see a very short code which implements principal component analysis. Here you can see that I'm trying to import a bunch of important libraries. Pandas and NumPy are basically Python libraries which you use to manipulate your data, load your data, and work with your data. Random is another library that we are going to use to generate some dummy data for this particular example. Then we are importing PCA, Principal Component Analysis, from scikit-learn. Scikit-learn again is a very commonly used library in Python, and we also need to do some pre-processing. I will tell you why pre-processing becomes extremely important, and then we'll try to visualize whatever PCA we have carried out. Okay, so for that we are importing matplotlib. So once all these import statements are run, I'll just run it again. It runs. Now we are trying to generate the data on which we will carry out our principal component analysis. First, I'm dynamically naming, I'm creating an array, which is nothing but a list of names. So gene plus stri, where I is in the range of 1 to 101. So it will basically give me an array with values like gene 1, gene 2, gene 3, so on and so forth. So that is just to get the column names, the row names is what I'm trying to do here. And WT and KO, you can just think of them as whatever column names you want to give. Here, I think I've just pulled this code from the internet, so I don't know what the WT or the KO stands for exactly. But it basically could mean, let's say you could say that this is math marks, or it could also be science marks, right? Just to illustrate, and instead of gene, we can have students, right? So now if I run this, I think, yeah, I need to specify this here. I need to change this as well, math marks, and let me do it really quickly. And for KO, we'll just change this with science marks, right? So I think the idea is very clear. Now we have a data set where we have a bunch of students, and for all those students, we have a lot, like a 5 different types of math marks. Let's say they have, okay, they seem to have like out of 1,000 or out of 1,100 paper, which is funny. It doesn't really represent the variables very well, but let's assume that we have multiplied their marks by 10 or whatever. So these are different math exams that they wrote, and there are like 5 different science exams they wrote, and these are the students. What I'm trying to do here is display the information that I've built. I'll really quickly touch upon this piece of code here. So what this piece of code does is it randomly creates, uh, it is basically randomly creating these numbers for you. This is the range of the number. So we are also mentioning that, okay, this is what the range of the number should be. No, wait, actually here we don't really mention the range of the number. We mention the mean and the standard deviation, right? So that's what we try to mention in np.random. So once we have given the distribution of the data, it is creating a bunch of random numbers for us with a certain mean and a certain standard deviation. So that is what this piece of code does. And by data.head, I'm just trying to look at the first 5 rows of data of the data frame that I've just created. And with data.shape, I'm trying to print that, hey, how many rows of data is there and how many columns of data. Since we have 100 students, there is like 100 rows of data is there. And since we have 5 mathematics exam marks and 5 science exam marks, we have 10 different columns. So this is what the data looks like. Now, this is a very important part, right? So we need to scale the data, and scaling needs to be done for two different things. First of all, like if you remember while discussing this particular example at the top, I mentioned that we are also centering the data, right? The data is actually located in the first quadrant, but we are shifting it in such a way that it is now centered across the origin. So that will generally happen if the mean of the data is zero, right? Right? If the mean is zero, but at the same time, we also want the data not to be too spread. Like let's say, if I take my math exam out of 1,000 and if I take my science exam out of 10 marks, right? So then automatically a lot of information bias will be toward math marks because the numbers will be bigger. So we need to scale that data. Otherwise, our principal component will be dominated by that particular variable, which has a larger order of magnitude. And that's what we are doing here. We are first using preprocessing.scale and we are passing it data.t. Why data.t? So yes, why not data? So the idea here is that preprocessing.scale accepts your data row wise. So we need to pass one row of data at a time. And this is how you pass a row of data of a NumPy n-dimensional array. And that is what we are doing here. Data is nothing but a NumPy n-dimensional array. And we are passing it the whole data, but one row at a time. Then we declare a new object of PCA. Now, what is this object? Why are we creating an object? Why don't we simply have a function? So you create an object by doing it something like this. You call that object and you open and close the parenthesis. The idea for having an object and not having a class, function here is because you want to first find the principal components for a certain data, but after that you also want to transform using those lines. So once you have found the principal components, you also need to bring your data to a lower dimension. So for bringing your data to a lower dimension, all these data points are then projected on these principal components and you get your new PCA data. So if you started with a, let's say, 100 dimensional data, we will get down to 10 dimensional data. So this is what you do when you have to specify, uh, that I want to transform my data. And that's why we need to declare an object, because once you have trained this PCA.fit, if you want to store this, you can store this. If it were a function, then you would not be able to store it and then use it on a different test data set, right? Generally, what we do is we have a training set and a test set. So you need to do this in order, to do for the fact that you first need to train the principal components on your training data, transform your training data, use it in your ML models. Then when you are testing it on a certain data set, then you want to use the same principal components that you had developed initially on the training data. And you need to pass your testing data to those principal components and get the value. So that's why we need an object. So we run this and it runs. And then in this step, what we are trying to do is we are trying to generate a scree plot. Now, what is a scree plot? So this is going to tell you that what percentage of information lies in which principal component. You see, we started with a data which was 10 dimensional. We had like 1, 2, 3, 4, 5, and all the way till 10 different marks. But if you see here, almost 90% of the information that is there in those 10 different columns can be represented with just the first principal component. So that's the power of principal component analysis. Now what I can do is simply put n equals to 1 where I am defining my principal component analysis object, and my final data will become a one-dimensional data which will still have 90% of information that I had in my original data, and I can use this for prediction, for building a machine learning classifier model which tells me that which of these students are good students and which of these students need some help or some guidance. So that's the main use of principal component analysis, and it was like a really short tutorial and a really short code run through, but I think it captures the essence of principal component analysis. Thank you for listening to me.